Good afternoon, everyone. Today I'll be presenting a performance assessment on CPU algorithm. This is my OS project. So our research project mainly focuses on scenario-based approaches to evaluate three fundamental scheduling methods, which are first come, first served, round robin, and shortest job first. This is the presentation made by me. My name is T. Siddharth. So now we are going to look the overview of this PPT. First, we'll be discussing about the authors, and next the introduction. Next, detailed information about the first come first serve. Next, detailed information about the shortest job first. Next, about the round robin. This study was collaboratory effort by these six authors, and they represent the Department of Computer Science, and they are from the Al Mar Marfa University in Saudi Arabia. So this is the details of the authors. Next, we'll be looking into the introduction. The primary challenge in computing is efficiency in CPU scheduling. It is vital for maximizing utilization and throughput while minimizing response times. Our study evaluates FCFS, round robin, and SJF algorithms using an innovative scenario-based Java simulation. Our specific goal is to analyze how dynamic quantum size affect round robin efficiency compared to other models under unpredictable real-world conditions. This is the problem. This is the scope and innovation and goal. So we'll be discussing about the three layers of the CPU scheduling. First one is the long term. So long term determines the which program which program is needed to be loaded into the main memory from the persistent from the storage. It will be loaded into the RAM. And the next, the medium term is that this handles the swapping process between the RAM and the disk from when memory is full. And next, the short-term memory, short-term layering is scheduling is like this is a CPU scheduler itself, which decides which ready process gets the processor next, which processor gets the CPU next. Next will be next the defining scheduling performance matrix. We need to know about these main to know the matrix. So matrix. The first one is the response time. It means the time from arrival to the first response generated. Next, we need to know about the turnaround time. It is the total time from process arrival to the final completion of the process. And next one is throughput. It is the number of processes completed per unit of time. Next one, we'll be discussing detailed about the first come first serve. Here it is an non-primitive algorithm, uh, like where processor handled in the exact order they arrive, like which will be first come will be served first. So much like a first in first out queue, we'll be using the same conditions in this. Due to this, we'll be getting a convoy effect. This convoy effect means where a short process are stuck behind the very long process, leading to poor CPU utilization. Here it is an example of the first come first serve. Uh, Here there are three processes, and we are also given the duration and the order and the arrival time. The first process duration is 24 minutes. So this is the grand chart, and the first process occupies the first 24 units. And next, the second process gets the CPU after the first process completed. So first process waiting time is 0, and second process waiting time is 24, which is the first process one, and the third process gets the CPU after the first process and the second process completed. So we'll be adding these both. So we'll be getting 27 units of waiting time for the third process. So to calculate the average waiting time, we'll be adding all these divided by 3. So we'll be getting 17 as the average waiting time. So by using the first come first serve, we'll be getting 17 as the average waiting time. Next one. Shortest job first. Shortest job first gives prioritize tasks with the smallest execution or burst time. While it is the most efficient at reducing the average waiting time, it has a significant drawback, which is called starvation. Due to that, long processes may never run if a constant stream of short tasks are keeps jumping into the front of the line, because the only the shortest job uh, present in the queue will be executed first. So due to that, we'll be getting a disadvantage of starvation. This is an example. We are given four processes, P1, P2, P3, P4, and we are given the burst time 6, 8, 7, and 3. Now we'll be seeing the Gantt chart. So first, P4 process is having the burst time 3. So first it will be executed, and next one is process P1 will be executed. And it is having the second least burst time. So P1 will be executed. So will be first process waiting time is 0. Second process the next P1 will be getting after 3 units of time. Next P3 will be getting after 6 plus 3 9 units of time. Like that will be going on. So next the next shortest one is the process P3. So it will be executed. The next process is process P2, which is the highest one. It will be executed in the last. So first process will be getting 0 as the waiting time. Next, the process will be getting 3 as the waiting time. The next process will getting 3 plus 6, 9 as the waiting time. The rest, the next process will be getting 9 plus 7, 16 as the waiting time. And the last process will be completed after at 24 units. So the average waiting time will be 3 plus 16 plus 9 plus 0, which is divided by 4 as it is 4 process. So we'll be getting the average waiting time as 7. So by using the shortest job first, the shortest job will be implemented first. Next one is the round robin quantum time analysis. So round robin is a primitive algorithm designed for time sharing. Each process gets a time quantum. The time quantum plays an important role here. So, if it isn't finished, when time expires, it moves to the when a process comes and gets some time quantum. If it is not finished, then it will again go back to the queue, end of the queue. This creates a trade-off. A quantum that is too small leads to a excessive content switching, while the quantum which is too large acts exactly like an first come first serve. Uh, Now we'll be looking into the example. So we are having three processes P1, P2, P3, and we are having burst times as 24, 3, and 3. So first we'll be looking to the Gantt chart. So first the process P1. Here the time quantum is 4. So first the process P1 gets into the queue and it will be executing up to the 4 units, and it will be passing to the next process, which is P2. So P2 will be executed for 4 units, but it only required 3 units. So it will be using some and giving to the next. So next process is P3, so it will be coming into the line. So the P2 process here has completed, so it doesn't enter the waiting queue again. It doesn't require the CPU again. So the next process P3 will be entered, and it will also be completed as it is only 3 units. Uh, so next again the P1 process P1 will be completed because only 4 units of P1 has completed. So remaining 20 units will be again be shared like this, like again from 10 to 14 again P1. Again it will not be completed. It will be having again 16 remaining. So it will again enter the end of the queue. So it will be again decreasing up to 4 units. Again, it will be entering the queue. Like that, it uh, continues till the process gets finished. This is the round robin example. The next one, in this experiment, we'll be doing the next slide is experimental design and simulation. In this project, our simulation was built in Java using the Eclipse IDE on an i7 system. We have used eight dynamically generated process for the runtime per run with random arrival and burst time. We have tested specifically with three different quantums for round robin, like 1, 5, and 10. These are the different quantums to measure the impact of context switching. And arrival times ranged from 0 to 20 units and burst time from 1 to 10 units. So we have also used the generate random times function. This custom function was created to produce arrival time and burst time. Uh, the next one. Now we have in this project they have used 5 scenarios. The study tested the across 5 distinct operational loads. So, first scenario is high burst time plus steady arrival. Uh, we featured an which featured high burst time and steady arrival. Next, the second one is short burst time plus strategy spread out arrival. The third scenario is mixed burst times plus early congestion. The fourth scenario is moderate burst time plus evenly spaced arrival. The fifth scenario is short burst times or plus delayed arrival. Next, we'll be checking the results. These are the results of the average response time. Uh, the SJF shortest job first algorithm consequently achieved the lowest possible response time by prioritizing shortest jobs across all scenarios. This is indicated by the red mark. In these 5 scenarios, it is the least, so it becomes the best among these three algorithms according to the average response time. Next one is the RR, round robin. With quantum one, first we have performed, but it is given an worst cases. So almost all scenarios due to excessive contact switching overhead. Due to the low quantum, there is a very lot of contact switching. Due to that, uh, the round robin quantum one is indicated with a blue line. So we can see that in the five scenarios, the round robin with quantum one has the highest average response time, which means it doesn't. It's the worst. It's the worst case. And the next one is quantum influence. As we have increase the quantum value from 1 to 5 and 5 to 10, the performance became the performance began very giving best outputs, which especially matches the SCFS, uh, which leads to give the short burst times. The quantum number 10, Q is equal to 10, gives the round robin. In round robin is indicated with orange one. Here we can see the orange one. Uh, all the orange one is like all the orange bars are in the five scenarios. The orange bars are nearly same with the FCFS, first come first serve. So the in the round robin case, when the quantum is increased, it is showing the best outputs, and it is also the outputs are also similar to the first come first serve, and it's the first come first serve. Uh, in this one, we are having it is effective when arrival order was favorable but struggled in the third scenario, like congestion. So due to that, it is an medium role in this average response time. Next, this is the analysis of the average response time. Shortage of first has the least response time, so it is in the leading, and the next one is the shortest first come first serve. It is the second shortest, so it is the second one, and our round robin case where in round robin case where quantum is equal to 10, it is performing well. So this is the third one, and the worst situation is the in round robin where the quantum is 1. So this is the analysis of the average response time. Next one. Next we'll be going to check the results of the average turnaround time. In this turnaround time, the here also again the shortage of first shows the dominance. It provided the best turnaround efficiency because it cleared the queue of shortest job rapidly. The next one here we can check that the red one is again the least giving the least turnaround time. So this is the best one again. The shortage of wins again. The next one is the first come first served. Uh, Here it performed well, but in scenario two, we had a slight high turnaround time in scenario three, but because early long burst process delayed everyone else. So uh, here we are having the shortage of first come first served as the second least one. So this came again second. The next one is the round robin. In round robin, here the red one is like no, the orange one is the quantum number 10 for the round robin. So it again played an good role when quantum is 10, and it is again worse when the quantum is 1. This is the blue line. So we can check like that. Next one, here is an analysis of turnaround time. The shortage of first SJF again won this. And next, the second one is the first come first serve. This is the second one. And round robin with quantum 10 is the third one. And round robin with quantum 1 is the worst one again. Next, conclusion and the future works. Uh, so here the in conclusion, there is no one size fit all algorithm. The SJF is the best in burst time are known, but RR is ideal for the for time sharing if the quantum is balanced, and first come first served works for uniform task. Looking ahead, we aim to use machine learning to predict optimal dynamic quantum sizes and develop hybrid scheduling approaches. Thanks for your time. This is the end of this PPT. Thank you.